Languages. A beautiful way of arranging characters into words and words into sentences. It is so powerful that we can weave imaginations out of sheer words and phrases and share intimate feelings. But the question is, how can machines understand and map meanings? How can we make machines autocomplete a sentence? How can we exploit our understanding of time series models like RNNs and make bilingual bots well equipped to translate? So fellas, fasten your seatbelt, cause we gonna answer all these questions and covering various papers on machine translation. Now up until 2006, n-grams had been the favorite pick for language modeling as well as statistical machine translation. For instance, in the paper by Marino et al., he describes how we can make use of n-grams of source target tuple to learn the translation model. What's source target tuple? What's translation model? Now let's say we are translating from English to French. Then English is the source language and the French is the target language. Now Marino talks about having tuples of mapped English-French phrases. A set of shortest phrases which provide the same monotonic segmentation for sentence pairs are mapped in this approach. It can have null translations and may also require internal reordering. Now they build the final translation as a combination of 4 features. 1. Target language model. This is a simple n-gram based next word predictor. In the target domain, which is French here, it is plain with a bit decoding of conditional word probabilities, which means finding the words which maximize the product of conditionals in a sequence of word probability distribution. A word bonus model. This is to overcome the machine's soft spot for smaller translation, which makes it incorrect. In short, making it longer. Third, source to target lexicon model. It is learning alignment AJ for the target. So if the languages are perfectly aligned, then AJ is equal to J. Otherwise, AJ can be any value like J-1, J+1 or so on. Fourth, target to source lexicon model. In this case, we will be learning complementary translation model. So the alignments to be learned are for the source here. These are the 4 features which are combined, and we also learn the weights of this feature combination which yields the best result. Think of it as more or less like grid search kind of thingy. But the picture starts to evolve with the work of Holger Swank in 2012, where he describes the neural network based training which has common hidden representation. This is quite significant from the point of view of laying foundations for encoder-decoder networks. He uses 7 words as input and output, plus he uses the null word to accommodate the variable length phrases. They try to simplify the conditional as shown in the figure and also use multiphrase perplexity to measure the performance of translation. For each sentence, this is nothing but the geometric mean of target word probabilities conditioned over the source words. Now, post 2012, RNN started to pick up in a big way, and if you believe the inside rumors, there was a publication explosion where all the HMM and time series papers were redone using RNNs to get the state-of-the-art results and therefore get quickly published. This is one of the reasons why deep learning has got a bad name and is termed alchemy. But the work of Zhou et al. Was not at all like that. Before discussing the paper, let us understand what is an RNN, what is LSTM, and what is GRU. Recurrent neural networks are just the deep learning models with self-loops. They can be best explained by unrolling the loop in time. So in some ways, we are introducing new weight edges in the model, which connects the feature map with itself along the time axis. In 1986, Jordan proposed a way to use context as a memory element to learn and improve the system output. Now in this approach, these recurrent units are not learned. The backprop only affects the remaining non-recurrent unit. It kinda reminds me of autoregressive models which we use in signal processing. The simplified alternative to it was provided by Ellman in 1990, where the hidden context is recurrent over itself. But the real deal of math insights came from diploma thesis work of Sepp Hochreiter in 1991, who described the problem like vanishing gradients and exploding gradients for deep learning and RNNs. 6 years later, in 1997, Sepp himself proposed an elegant solution to this gradient problem by envisioning long short-term memory. The structure of gating mechanisms makes it immune to the exploding gradient problem. Now of course, this doesn't guarantee the stability in terms of learning. The key recurrent component in LSTM is memory cells. Let's say there are some 10 odd units in the cell. Then maybe 2 units can carry long-term info and the rest of the units can carry short-term memory info, which is why it is called long short-term memory. These cells are controlled by gates. The forget gate is deciding which units to keep short-term and which ones to keep long-term, and the sigmoid gating is multiplied to the previous cell values. The gating is learned in terms of linear combination of weighted input and hidden units. Think of the input and previous hidden units as dominant controllers who are deciding all kinds of gating. The second gate is again decided by the same controllers. The difference is only in terms of weight matrix and the placement. It controls the influx of information, which is why it is called input gate. The influx is based on C tilde or the 10H version of weighted combination of input and previous hidden units, aka the controllers. Now, why are we using 10H and not sigmoid? That's because 10H allows for non-binary values for weight increment. The last gate is the output gate, where the weight combination of controllers decide what should be my next hidden unit. Now, one popular variant of this model tries to tie the knots between input and forget gate. This means you only modify short-term cell units which are meant to be forgotten. The input and the forget gates are therefore complementary to each other and share the weights. The recent work of Cho et al. In 2014 brings about tectonic shift in the structure for tasks such as neural machine translation. It not only couples the input and forget gate, but even gets rid of the separate need for memory cells. As you can observe, a 10H version of the previous hidden unit H and input yields H tilde. The coupled input and forget gate is what they call as reset gate, and it decides the fate of each unit in the cell. It can decide whether the hidden unit should be affected by the H tilde or they will carry on and propagate the long-term info. The paper by Cho attributes the success of its translation model to these changes in recurrent units. They term this modified recurrent structure as gated recurrent unit. The simple recurrent neural network does not have any of these gates and is simply using the previous hidden units along the input to get the current hidden unit. The notable variant to it is presented by Schuster and Paliwal in 1997, where they talk about having hidden units as a function of both previous and next hidden unit, which is why they termed it as bidirectional RNNs. So there are these forward hidden units and backward hidden units which are recurrent in different directions of flow. But you know why RNNs suck, right? Exploding and vanishing gradients. That's why I came in bidirectional LSTMs, where the only change is that the forward and backward recurrent units are being gated as per LSTM instead of simple RNNs. Now, zooming out of the theory, let's look at the approaches for neural machine translation which made use of these variants. To design an encoder, you can simply look at different context modeling for recurrent structures mentioned earlier. Let us have a look into work of Cho in 2014, where he's having gated recurrent unit. This means coupled input and forget gate plus the absence of separate memory cell. Now at first, the 10H operated version of weighted context vector is compared with the 0 vector output embedding. After this, the recurrence in the decoder part is just quite similar to that of an encoder, where instead of input and hidden units controlling the output, we are having 3 controllers. They are A. Context vectors, B. Previously used hidden units, and C. Previously used output word embeddings. The above 3 are controlling both the reset and update gates. They also control the values of prospective hidden aka H tilde. Now after you get these hidden units, the most intuitive thing is to express this output word probability as a softmax operation over the weighted combination of context, current hidden and the previous output. That works, but a smarter strategy is to use a trick called max out, which vomits out 2 probable hidden units from one. So we take the max of these twin units in an element-wise fashion followed by a softmax, which yields us the class probabilities. This max out kind of split allows the decoder to have a multimodal perception of the decoded word. It also helps to get rid of overfitting. Now some of the experiments, like the one conducted by Sutskevar et al. In Google Research Group in 2014 NIPS, also points out the advantage of reading the sentence in reverse. This helps because when we are decoding the first target word, the context will be closer to the first source word and not the last one. The paper talks about this as introducing short-term dependencies for large sentences. They also use end of the sentence tag to stop decoding. Lastly, let me talk about the paper from Bengio Group in 2016 titled Neural Machine Translation by Jointly Learning to Align and Translate. This paper talks at length about the limitations of having fixed context representation for a sentence. Especially if the sentence is very long, it is difficult to translate correctly. With this in mind, it introduces bidirectional RNNs followed by attention mechanism to jointly align and translate. The idea is simple. Why can't we combine the hidden units for all the words softly instead of having a single context vector? So the alignment is learned as EIJ, which is tonnage over the weighted combination of the decoder's previous hidden unit and the encoder's hidden unit. This acts as a moving bridge between the encoder and decoder's hidden unit. So for 3-word source input phrase and 5-word target output phrase, EIJs will be nothing but 3x5 matrix. Now the softmax normalized weighted combination of these EIJs is what we call as alpha IJ, which is again a 3x5 matrix. The use of this alpha IJ is to generate context dynamically for each output word. This is by a weighted combination of input and hidden representation. The use of this alpha IJ is to generate context dynamically for each output word as a weighted linear combination of input and hidden representation. The weights are given by the same alpha IJs. So for the second word in target output, my context will be based on linear combination of encoder's hidden units with weights given by alpha I2. The rest of the decoding is more or less similar to the conventional approach which was used by Cho et al. In 2014. The visualization of this attention weights also tells us about the model's understanding in reordering a word in a new language. Now as you can see, this anti-diagonal line strip means that the words are flipped in the translation, and the vertical strip means that the same word in the source maps to 2 of them in the target domain. Summary of research papers related to neural machine translation. I hope you like it. Please share it with your friends and research buddies interested in statistical machine translation. So see you next time. And don't forget to subscribe the channel and press the bell icon to never miss an update from Crazymuse.